Okay, in this short series we'll be going over different ways graphs of functions can be transformed. Of course, we'll only have time and space to look at a couple of examples, so it's important you catch the main ideas, and hopefully the examples we do will illustrate those ideas clearly enough. From perhaps years 9 and 10, you started looking at curves like y equals x squared. You saw that adding or subtracting a number at the end of the equation had the effect of moving the graph up and down. If instead you added or subtracted a number inside the brackets as shown, the effect would be to move the graph from side to side. What might have been weird though was that this time it behaved in perhaps the opposite way to what we'd expect. Even though it's a plus inside the bracket, and positive numbers would feel like they point right on the x-axis, the graph has actually gone left. At some point you may have just memorized this as a pattern, that going up and down seems to behave normally while side to side behaves weirdly, and this would have been awful when moving graphs like circles around where both directions seem to behave in the opposite manner. You may have then accepted that these things in brackets behave weirdly, which while generally true might not be the most satisfying thing to memorize. So what's actually going on here? Why is it that sometimes things go opposite, sometimes they don't? And we'll illustrate this by first looking at this circle that has moved 3 across and 1 down. The first thing to notice about this equation is that it's really following the same pattern as the equation of any old circle that hasn't moved at all. Here, we'll blank out what's in the brackets to see what I mean. It's just something square plus something square equals 1. And that's just the Pythagoras pattern, which is why it traces out a circle in the first place. So really, the form of the equation is no different from the plain old x square plus y square equals 1. And because of this, we should say, for now, that nothing has happened to the circle. It's just that x itself has changed into x minus 3, and y itself has changed into y plus 1. And here is the main point of this video, and what I feel is actually the most important idea to get across in this whole series. It's that to make sense of this entire topic, and do trust me on this, whenever the form of the equation doesn't change, but x and y themselves have become something else, well, that's going to redefine what x and y mean without changing the curve itself. And the effect of this is to transform the axis instead of transforming the curve. And I will write this down somewhere, it's super important. Okay, and let's get back to the graph to see what we mean by that. So let's start with the plain old x squared plus y squared equals 1. Now this is the Pythagoras relationship between x and y, sweeping out the circle, centered at the origin with radius 1. Now we change x to x minus 3, which again is a transformation of the axis. And so the axis is going to move 3 to the left. That's where minus 3 still means 3 to the left, but it's the axis moving, not the curve moving. And now we change y to y plus 1, which again is a transformation of the axis. And so plus 1 applied to y still moves upwards, but it's the axis moving, not the circle. And it's only as we recenter the camera and think about where the circle used to be, that it looks like it's gone right by 3 and down by 1. But really, it's the axis that has moved, and only because we insist on keeping the axis centered, it looks like the circle has appeared to move the opposite way. Okay, you might want to watch that again to see how the axis transforming makes the graph appear to move in the opposite direction. Okay, but that's the important thing for this example. Let's return now to the parabola. Maybe a question we now have is why in some cases things did appear to go in the expected direction. So it's not always the axis moving, maybe. Now notice that the equation begins with y equals. This means in this equation, we happen to have direct control over the y value. Okay, if we add 2 to the end, well, the y value gets boosted by 2, and so the graph goes up by 2. Right. Note that y and x themselves have not changed at all. Okay, so you can still see the y has been left alone. The x square is still just x square. It's just that we've added 2 to the end, right? And this really was only meaningful and only pushed the graph upwards, right? Because the right-hand side just so happened to directly control the y value. And that's only because the equation starts with y equals. Okay? Note that the circle's equation did not look like y equals something something. Right, so it wasn't possible to control the circle in this way. That's why for the circle, even in the vertical direction, the only control we had was moving the axis. Okay, because it didn't look like y equals, and so we had no direct control over that y value. Okay, so pause here, rewind if you need to, just to make sure you're really okay with the difference and what's happened so far, because we're about to see the same thing in a slightly different angle, so it would help to be clear on everything we've talked about so far. Okay, so let's draw the same graph on the right here, but this time we'll rearrange the equation by subtracting the 2 to the left-hand side, so it looks like y minus 2 equals x squared. Now this just looks like the plain old y equals x squared, except this time y has been changed into y minus 2. And so this has the effect of changing the axis. How does it do that? It subtracts 2 to the y, and so it's moving the axis down by 2. But this effectively is the same as what happened with the graph on the left. Right? See, if we return everything back to original for a moment, the only difference between the two ways of seeing this equation is that on the left, the curve gets pushed up, but on the right, the axis gets pushed down. Clearly, if we just realign the axis, the graph hasn't changed, and of course it can't have. Obviously, the equations are algebraically the same thing, but I hope that helps illustrate the slightly different ways in which we can think about controlling or transforming the graph. Okay, I know the one on the left might seem more natural, but actually I reckon it happens by coincidence, right? Again, it's only possible to control the graph in that way when we just so happen to be directly controlling the y value in the equation. Changing the axis is generally more powerful and versatile, and also it's really important in solving problems in practical contexts, like in physics, or even when studying like motion later in our maths courses here. Okay? Alright, so here's a summary you can write down if you're into that sort of thing. Whenever x or y becomes something else, okay, without changing the rest of the form of the equation, it redefines what x and y mean, and therefore transforms the axes. Okay, so either the x or the y-axis, depending on which one or whether both have changed. The graph then appears to transform in the opposite manner. Okay, so for example, if y equals x squared becomes y equals x plus 3 or square, then x has become x plus 3, so the axes have gone right by 3, so the curve would appear to have moved left by 3. Okay, so let's combine what we've done to graph this parabola. We start by thinking about the plane y equals x squared. Okay, we draw that in yellow here. We can then think of the x changing into x minus 4. Okay, that's going to move the axis left by 4. Okay, minus 4 going left by 4. But now that we get the hang of it, most of the time we'll stop talking like this, and look, we'll just say for convenience sake that the parabola goes right. Okay, we're going to sort of skip the axis moving quite quickly. In the back of our mind, we know it's the axis moving and so on, right? But it'll just make it easier to talk about how the graph has been transformed, right? Even if we now know better. Okay, I can't stress enough though that you've got to make sure you understand exactly what's going on, okay, for what we do later. Alright, the negative one at the end is applying directly to the y value, so it pushes the parabola down by 1. Okay, the formal way to talk about the graph moving is to call it a translation. The parabola has translated 4 units right and 1 unit down. And the best way to indicate this for a parabola is that we often label the vertex, so here it is at 4, negative 1. Okay, so that's translations, moving the graph and or the axis by adding or subtracting numbers. Okay, once again, just be careful with whether those additions or subtractions are directly controlling y or x values, or whether x or y themselves are being changed. Okay, that affects whether it's the graph that's moving or the axis that's moving, and therefore whether the motion in the end should be reversed or not. So thanks for watching. Of course, rewatch any bits you don't feel you fully understand yet, and feel free to ask further if you have questions. See you around.